Okay, good afternoon. My name is Kangrou. I'm a postdoc at Tsung-Dao Institute, Shanghai Jiao University. First, I'd like to thank the organizers for giving me the chance to present because due to my careless mistake, I forgot to submit my abstract. But today I'd like to talk about the formation of free-floating planets via planet-planet ejection. We actually started this project after Ida-san presented some preliminary results at the last Vogue World Conference in Osaka. And after 1 year, it's finally in a much better shape. So I'm happy to talk about it today. So since we're a free-floating planet themed conference, I don't need to spend time explaining what free-floating planets are. And we're all very familiar with this figure. Does this work? Okay. This figure have appeared in multiple talks in previous days. So we know that the mass function of the free-floating planets can be best fit by this very nice power law function. But despite of this neat form of this mass function, we still don't know its origin. And there has been many mechanisms proposed to explain the formation of free-floating planets. I've listed a few here, but I believe I haven't covered all of the mechanisms that were discussed in this conference due to limited space. So in this work, we focus on planet-planet scattering in single-star systems. So the questions we're trying to answer are first, can planet-planet scattering in single-star system explain the observed free-floating planet mass function? And also, how do the predicted bound planet population compare with the microlensing survey results? The reason I emphasize on single-star system is because first, of course, the population synthesis model here we use is designed for single-star system. But more importantly, for planetary systems around single stars, we have plenty of observational data so that we can compare our results with them and so that we know if our model is good or not. So this is a brief introduction of how planet population synthesis or PPS model work. For those of you who are familiar with the Burn model in GPPS, you already know how a PPS works. So we have observationally inferred stellar and disk properties that are used as initial conditions for our planet formation models. And our formation model includes different processes like oligarchic growth of embryos, planet migration, gas accretion, disk evolution, and planet-planet interaction. And all of these processes are prescribed with semi-analytical formula in the IL model, the Eden-Lin model. And these formula are based on either first principle calculation or expensive numerical simulations. So we use a Monte Carlo approach so that the computational costs can be significantly reduced. We can do simulation of thousands of systems within like a few minutes. So we get this synthetic plant population that can be compared against observation, and we can, from the observation, we can calibrate our model, and we can also predict or explain the observational data. Now, since we're talking about ejecting planets, the stellar mass is an important factor we should consider because it determines how tightly bound a planet is and how easily it can be ejected. So the original IO model is designed for solar type stars and it uses a Gaussian distribution of stellar mass given a center. You can input any value for the center, but the microlensing survey targets stars towards the galactic bulge. So these are typically lower mass stars and they're older. So in order to make a fair comparison with the microlensing results, we need to consider a consistent stellar initial mass function for our planet formation models. So we consider this broken power law following Sumi-san's paper. We consider this broken power law from Hoshimoto et al. 2021. The PDF of this mass function is shown on the figure in the figure on the right, in the green curves. Those are the red curves, and we consider a more conservative stellar mass range from roughly brown dwarf mass to 3 solar masses because we don't have enough understanding of how planet formation goes on around like very low mass or very massive stars. So we're sampling about 66% of the stellar mass sample as in Sumi et al. 2023. So I'd like to explain two mechanisms in our model to eject planets. First, we have migration of giant planets. So the orbit spacing of two planets delta is given by the mutual distance scaled by their mutual Hill radius. And this delta can decrease either when two planets undergo convergent migration or when one planet grows. So its Hill radius expands. And in the two things can happen when delta decreases. So in the not so strong scatter regime, we have repulsive scattering, where the eccentricity of the smaller planet is increased and is then damped by the disk, so that both planets move inward together, and this is called shepherding by giant planet. Or in the strong scattering regime, we have close encounter, and the eccentricity of the small planet can be ejected beyond unity, and it's ejected from the system. So this is ejection in the disk phase. A more dominant mechanism is planet-planet scattering after the disk dissipates. So basically, secular perturbations determines the orbit crossing timescale of the planets, and their eccentricity slowly builds up. Finally, the orbits start crossing, and we have scattering and ejection of planets, or actually collisions also included. So these processes are prescribed in the Eden-Lin model with a Monte Carlo calculation, and the prescriptions are calibrated with a large number of n-body simulations. But since we're considering a new stellar initial mass function here, we'd like to also confirm with n-body simulation that the prescriptions are good. So this is our simulation setup. We have three different sets of simulations. Set A is a large sample, consists of 3,000 stars. This is a big sample that allows us to compare against the observation. And we also have smaller sample sets B and C to allow us to compare for the purpose of comparing n-body results and Monte Carlo results. So these are, I listed some key parameters in our formation model. Because of limited time, I don't want to dive into the details of these parameters, but I just want to emphasize that these are not crazy parameters. We didn't fine-tune anything. These are just very standard values that are widely used in previous literature. And then after the disk dissipates, we have a dynamic evolution phase. For sample A, we just use the Monte Carlo prescription, and for set C, we run n-body simulations with the rebound code. And then we can get the distribution of planets in the symmetry axis mass plane, and also their mass function to be compared against the microlensing data. Then I'm showing our results for set A, which is the big sample. So on the left, I'm showing the distribution of planets, the bound planets on symmetry axis and mass plane. And the figure on the right shows the density distribution of the data points in the left figure. And I color-coded the planets to be different types, including gaseous, rocky, and icy planets. So from the distribution, we can see that giant planets are actually very rare because the majority of the stars are low-mass stars. You can see from the density distribution here, the gaseous planets are very rare. And the planets within the mass range of about 0.1 to 10 Earth masses are the most abundant type of bound planets. And then we can look at the ejected planets. Similarly, I'm showing in the left panel here the distribution of the pre-ejection values of the symmetry axis and mass of the eventually ejected planets. And in the middle panel, I'm showing the density distribution of the data points. And on the right panel, I'm showing a pie chart showing the contribution of different ejection channels to the ejected population. So these results tell us, the different ejection channels are listed here. So we have secular removal, which means that the small planets are considered removed when multiple giant planets become unstable. And by small planets, I mean that the ratio of their escape velocity over the Keplerian velocity is smaller than 1. So basically, they don't have the ability to eject planets out of the system. And also, we have embryo scatter ejection. Embryo means this planets that are smaller than 30 Earth masses, so basically non-giant planets. They scatter each other and eject another embryo. We also have embryo giant scattering. So this means that the planet is ejected by a giant planet, and also giant planet scatter them among themselves and eject the giant planets. And migration means that the planets, small planets, become ejected through the migration of giant planets. So we can see that the contribution from giant planets is actually pretty small. It's smaller than 40%, and the majority of the ejected planets are actually coming from embryo scattering, which is over 60% of the population. So now I'm showing the mass distribution of the bound planets in our simulation set A in comparison with the observational data. So I'm selecting the planets that are that fall into the range of about 0.1 to 2 Einstein radius, and plotted the mass function in this blue histogram, and compared with two different microlensing survey results. So you can see that the overall trend of this decreasing planet frequency with the mass ratio actually agrees pretty well with observation. And this is the comparison of the ejected mass function in our simulation against the observation. So the histograms are from our simulation. The gray histogram shows the combined mass function of ejected planet in our simulation. And we see that for the mass range larger than 10 Earth masses, our simulation results actually agree pretty well with the power law mass function. But for planets smaller than 10 Earth masses, our simulations predict relatively flat distribution, and the absolute values are actually a bit smaller than the observation. So this is my summary. With self-consistent initial conditions plus the stellar mass sampling, we can make reasonable predictions of free-floating mass functions. And for a smaller mass range, we produce lower FFP abundance. And but it's worth mentioning that the observation has high uncertainties in this smaller mass range. And the take-home message is that we found ejected Neptunes, which means like smaller planets under 10 Earth masses, dominate the FFP population, and we expect future observations will test this. And the paper is on arXiv. You're welcome to check the details. Thank you.
So it seems appropriate to use this Koshimoto mass function for the bound planets. But for the ejected planets, shouldn't you start with an IMF with all the high mass stars? Because they'll be, as they evolve, then, planets will be ejected from the high mass stars, but they'll still be, orbiting through the galaxy. So you might find that, most of the planet ejections come from stars that have ended their lifetimes.
You mean for like stars that are larger than about eight solar masses or so? We consider only up to three.
Well, yeah, I mean, stars that are, more massive than their solar mass, right? I mean, they can end up as white dwarfs or...
Yeah, because we are focusing on, planet-planet scattering within the planetary systems. So we want to make sure that our planet formation model is robust, reliable. But for very massive stars, we're not sure. I think the formation scenario is a bit different from what we consider here in the classical case. Because
it seems like those might contribute to a significant fraction.
Yeah, so this isn't the complete picture. Of course, we have free-floating planet generation in star clusters, and here we only consider single stars. So yeah, this is not the complete picture.
So can you go back to your figure comparing to the data? I think this was the previous slide.
Oh, sorry.
Hi, Scott Gowdy. So the agreement on the left is miraculous. Was there any fine tuning there? Or is that what just came out of your simulations?
For the bound planets?
Yeah.
No, actually didn't tune anything.
That's amazing. But the question I had is that given that, you can produce the bound planets perfectly, and you don't, but you get the normalization wrong for the free-floating planets, that strongly constrains the possibilities for how you could fix the free-floating planet problem. For example, you can't just pump up the mass of the disk, because then you would probably overpredict the number of bound planets. So have you thought about what possible ways what Dave mentioned is a way to do it, right? Which is you make get another source of the free floating planets that doesn't contribute to the bound planet population. But have you thought about ways of solving this discrepancy that doesn't screw up the bound planet population? It's a very powerful thing.
Yeah, we've tested a few other parameters. But yeah, I really don't think I've considered the problem in that aspect you mentioned. We're basically just looking at how, like higher disk mass or like faster migration changes the ejected mass function. And we found that the ejected planet mass function isn't very sensitive to the parameters we select. But yeah, so sometimes if you consider like less efficient migration or higher disk mass, we might overpredict the abundance of bound giant planets. But I think there's still some uncertainties in the gas accretion and migration prescriptions we use. So thank you.
Okay. We'll take one last quick question as the next speaker sets up.
Really nice talk. You say.
Oh, sure.
You say that you're just modeling planet-planet scattering for single stars. Is it the difference between your predictions and the observations as simple as in binaries, there are more ejections that could reproduce the observations?
Sorry, I didn't quite catch the.
Well, you're only simulating single stars,
yes,
right?
Yes.
And you're under-predicting the number of free-floating planets. So could this, excuse me?
For the smaller planet mass range.
Right. So is it as simple as binary stars likely eject a lot more planets?
Well, that's what William presented yesterday, right? So if you consider binary ejection, those smaller planets migrate inward and then reach the unstable region, could be ejected by binary star systems. So I think it's natural to expect binary star system would produce more like small planets that are ejected.
Okay, thank you.
Thank you.
Let's thank our speaker one last time.